Hello everyone. In this video, we will be building machine learning models on this dataset. However, the broader goal is to understand the process of building end-to-end machine learning models on any dataset. So to start with, you can go to the code section here and create a new notebook. I've already created one notebook and I've added some necessary input. Once you do that, the first step, of course, is to read the data. We can get links to that here. You can copy the file path, and here I'm going to use the read CSV from pandas to read these three files as data frames. Now we have our train and our test data. So the train is going to contain the labels as well, and we're going to use that to train our models and subsequently make predictions for the test. Now here the data sets are given to us in CSV files, but it is also important to know that data, even tabular data, can come in other file formats. It could be the TSVs or it could be XLSX for the Excel files. It could also be in some SQL databases. And it's important to be able to find resources online, at least, to be able to read those and then process the data the way we want. The other task could be sometimes the data can even be there as JSON files. So how do we think about converting those to a format that we want? So this is one of the tasks that I would say you can look up and see if Pandas offers any other methods as well to read files that are in a format other than a CSV. The next thing we are going to do is we are going to print a shape of the data set. So this gives a rough idea of the size of the data set. So we can simply do train.shape. But as I said, today we are going to focus more on building good end-to-end models, and that also means focusing on presentations. So I've already prepared a document, so I'm going to be pasting content from that, and we can make use of this to nicely say that we have about 58,000 rows and 39,000 rows respectively in the two data sets, and we have 13 columns in the training data, but the test data is missing the target variable. So to start off, we're going to go with train.head, and at this point we'll know that it shows the first few rows of the data frame, and this sort of gives an idea of the values that each column takes. This data set is quite simple in the sense that we are able to understand the features. Nevertheless, one of the important tasks is actually to be very familiar with what different columns mean. So here I've already gone ahead and added description of the various features. We have age of the person. So this is whether we want to approve the loan of a candidate or not. The details that we have in this data set are age, income, and then home ownership. Does the person own the home? Does he rent it? Is he paying mortgage to it? How many years has he been employed? Why is he asking for the loan? And then what is the grade that is assigned to the loan? There's a quality score that comes in different alphabets. Then the amount that is requested by the candidate, interest rate associated, and this is a combination of two other features. Has the person defaulted previously? Have they missed any payments? And what is their credit history length? And finally, the target variable. Now, at this point, though we understand these features, there's going to be a bit of domain knowledge that comes in, but we should not let it influence our decisions too much. We should still be able to read the data as it comes and then see what it communicates. That is, let's not come up with a conclusion and then build a model that fits that conclusion, but rather follow the process and see what story comes out. With that, the next thing we are going to do is we are going to see a bit more information about these columns. And here you can see that once again we have the same columns, and this also tells us what are the types of columns that we have. We have a few columns that are categorical. So here we saw that this home ownership took values like rent, own, mortgage, and such. And then there's also whether the person is defaulted. So this is going to be a yes or no thing, but even then we have it as a object data type. And then we have the loan grade, which again would have been alphabet. So this, what it tells us is how many categorical variables you have and how many numerical variables you have. And once we know this, if you the way we process these two features, types of features are going to be different. As we know, models cannot take in categorical variables directly. So later on, we are going to be thinking about how do we encode these different variables. So having an idea of what is to come is always going to help us. Now, once we have this, there's other information that is given here, which includes things like null values. And this is actually a clean data set with no missing values. But then this only takes into consideration things where it is explicitly stated as none in the data set. So individually, we would have to delve deeper into it. and see if the values are, say, marked as zero, if it is marked as blanks, question marks, if some other placeholders are used for null values. This particular function does not specifically capture that. Now, once you have this result, I would urge that you use the markdown cell to mention that, okay, these are my categorical columns, these are my numerical columns, I do not see any null values. So this is where we are focusing on the presentation aspect. So after the end of this notebook, I'm going to present a version of the notebook wherein we have written this and presented this well. The next function we're going to try out is trained or describe. Okay, so here, this is something that presents such statistics for the numerical columns. Now it has the things of how many rows are present and then your usual suspects of mean, standard deviation and different quantiles. Now this thing, it's not just some function that we have to put as a part of our notebook, but it is something that can direct what we do later. Now in this particular data set itself, if you notice, we see things like 123 as the maximum age. So is the case with person employment length. Now this is present in years and 123 seems like a ridiculous number for a person's age or employment length. Now this means that these are erroneous data and quite possibly 1 to 3 was just a number that was used as a placeholder when they did not have the value. And we would want to remove data points like this because it can negatively influence our model building. If we scroll further, we have our target variable loan status as well. And we know that it's a classification problem with two classes 0 and 1. And you will see that the minimum until the 75 percentile, we see most of the values are 0, but the maximum value is still 1. So this suggests that there could be some form of imbalance in our data set. We have to, of course, see this further. But right now it is telling us there's a possibility that your data set is imbalanced. And that should automatically tell you that you might be using imbalance handling methods in this particular data set. In general, when we use the describe function, we would want to get the most out of it. That is, we want to understand if there are outliers in cases such as this. What is the scale of our features? If you see the age, it is in a different scale. The values are between 20 and 123 in this case. Whereas if you take the income, it is in 42,000 until much larger value that is present here. So clearly the different columns are in different scale. And we've also learned in our courses that the scale of the data can also affect the model training. So there are some models that are affected by scale, some that are not. And this should also tell you that we should potentially be doing scaling of our dataset before we proceed. In some other cases, we might even see all the minimum 25th, 50th, all the way until the maximum value taking the same single value. And these are features where there is no variance. That is, the entire column takes just one value. And these are extremely useless when it comes to model building because they don't communicate anything new. So with that, the next thing we want to do is we want to see how clean the data set is. We already saw that there were no null values, but you can also use some other functions such as this to know individually. Here, once again, we see that there are no null values, but as I mentioned, we are not just focusing on this data set, but in general, the process. So now when you have missing values, you have a variety of options to deal with it. So you can choose to drop them, you can choose to impute them, and even imputing them comes with different methods. Do you want to use simple imputer, KNN imputer? Do you want to try and see if there are any other sources through which you can get data? These are some approaches you are going to have to consider when you're going to deal with missing data. Now, there are other supplementary videos which we can link if you would want to get more information on these processes. The next thing I'm going to do is I'm going to use this function called as MEV. And when we do this, it shows the number of unique values that each column takes. Now, the number of rows we had in the training data was exactly this, and ID column takes exactly the same number of unique values, which means that each row has a unique ID. And when it comes to model building, columns like ID are not very useful to us. So we can choose to drop this column later on. And if we recollect our categorical variables, we had person home ownership as a categorical variable, loan grade as a categorical variable. So is the case with loan intent. And this gives us the cardinality of these columns. Now, in this particular data set, we don't really have categorical columns with a high cardinality that is taking many unique values. But there could be many data sets wherein even the categorical columns could take a lot of values in hundreds or thousands or even more. Now, in these cases, when you're going to be using your encoding methods, you have to be very careful of which method to use. Now, if I use one hot encoder on this, on person home ownership, I'm still going to have four new columns that come up. Whereas if I had hundreds or thousands here, using one hot encoding is going to give me hundreds or thousands of new features, and that is totally going to blow up the shape of the data set with which I'm going to work on. So in that cases, can we consider some alternate encoding methods? Do we go with ordinal encoding? But we know that ordinal encoding has the problem of bringing an order to the column even when there isn't one. In those cases, we would also want to explore other methods. And now there are ones like target encoding, frequency encoding, and these are the decision choices we make based on the observations we get from here. So we can also individually check on different columns. So let's check one of them, person, home ownership. And I'm going to use this one called as value counts. And you can see it takes in these four values. So clearly there are a couple of values that this column takes that are more dominant as compared to the others. So if you had, say, a lot more unique values that this particular column took, we could again make a decision as to only keep the dominant categories and club the other ones to a single category. This can help reduce the number of columns if we were to use one hot encoding on this later on. Now, the other thing is when you actually check the values that each column takes, you might even see some other inconsistencies because real world data tends to have a lot of inconsistencies. Maybe they wrote rent as capital R and then in lowercase for ENT. Same is the case with mortgage. Maybe there was a spelling errors. So these are things that are going to come up when you try these, even these simple basic functions. So rather than just using these functions and having it in our notebook, we would want to make better use of each single function we put. That is, what does this function give me and how does it decide what I'm going to do later on. Now with this, let us start with a bit of exploratory data analysis. So exploratory data analysis, as it says, is a bit exploratory in nature, wherein we don't have a particular question in mind already. We want to try out exploration of different features, combination of features, and whatever results come from it, let us see if it is going to influence our model building somehow. So firstly, I'm going to start with the target variable and we'll do a value count for this as well. And if you see in our target variable, 50,000 entries belong to zero, that is the loan being rejected, and only about 8,000 is where the loan has been approved. Now this already tells me that the data set is imbalanced. Now in your previous courses, you have learned that when your data set is imbalanced, there could be some issues with model training. One is maybe your model does not find sufficient points for the minority class, which is why it might find it difficult to properly classify this class. For this, we can maybe use oversampling techniques, undersampling techniques, or we can use class weights when it comes to the models themselves, models which allow class weights, and even the evaluation metric that we use. So we've discussed that evaluation metrics such as accuracy might not really do well in the case of imbalanced data sets. Even a simple function such as value counts is already giving us so much information and is improving our decision making. Now these are just numbers. So we have this as 14% and this as about 85%. But let us also plot this and have a look at it. So for that, I'm going to use count plot from Seaborn library. My data is going to name and column is loan status. So in the initial run that we are doing, we're just going to focus on adding code snippets and understanding the use of it. But later on, we also have to focus on presenting them well because your target audience might not be people who are well versed in, say, machine learning or even interpreting these results that easily. Okay, so with this particular plot, we can clearly see a significant difference between the two. Let us also add a title saying distribution of the target variables. Okay. So with this, we see a bit about the target variable, and as I said, we have some observations of this data set that it is imbalanced. But in general, it can give us some idea of the distribution of the target variable and how to proceed with this. Now let's go with a bit of some univariate feature analysis. So wherein we are going to be looking at a few features individually. So for this, I'm going to paste a code snippet so you can try this out individually as well. But in the interest of time, I'm just going to paste some code snippets and we're going to go about. So here we have three categorical columns for which we have plotted the chart. And if you see the the distribution of different categories is fairly similar in the loan intent column. But if you come to both loan grade as well as home ownership, we see that there are a few dominant categories. In the loan grade column, it is mostly dominant by ABCD, whereas EFG are not really having that many rows. Now, of course, as I mentioned previously, one of the things we can do is do we want to club these categories which are not that frequent? So, but to do this, we also want to see how influential these categories themselves are. We are going to do it later. But this brings up an option that, okay, if there are categories that are not that dominant, then you can choose to club them into one category such as other. For example, maybe you have details of individuals across multiple countries. So there you are going to have over 100 countries. Or if you take even the case of cities in India, maybe hall ticket data, wherein students from different cities are going to be writing their exam, you're going to see plenty of these cities where the representation might be low, where there might be fewer people. In those cases, you might want to replace it with the state instead. So these are all options wherein you can sort of manipulate the data that you have to have lesser number of categories that you can work with. Now, with that, some other questions are we see that these are written with the alphabets A, B, C, D, E, F, G. So, in the case of, say, the banking lingo, does these grades mean anything? Do they have a natural ordering? So, can I convert this using an ordinal encoder? So, these are questions that should pop up when you see this particular plots. So, the next thing we are going to see is we are going to see if there are presence of outliers. So, for that, we can simply have a box plot. So, we'll start with, say, person's age. Okay, so here we have the box plot of person age, and as you can see, this is clearly an outlier. So even though there are all these points that are there beyond it, for these points we cannot be sure that these are outliers. But the case of this value over 120, we know from our experience that this is not something that is a valid entry. Now, likewise, we can even check for some other columns. Let us check for person income. And here, once again, we see a big separation. Most of the values are present between these two, but there are a significant number of entries that go beyond this table. Now, for this, how do we go about this? So again, now this is the place where handling different outlier techniques to handle outliers comes in. Firstly, we have to be very clear on what are these? Are these outliers or are these erroneous data? If these data are errors, then we can clearly drop them. But if these are naturally occurring in the data set, then we have to be a bit more careful. So we might have options of either transforming the entire column, or we could choose to cap these values to some high value. Here, instead of going all the way until here, we can say I'm going to cap if any value that is greater than 1 into 10 power 6, I'm just going to cap it as 1 into 10 power 6. So that is a choice you can make. Now, is this valid or not? You will only know once you train your model. Once you build your model, if it helps with your score, you can choose to retain it. If not, you can try out different methods. So once again, here you have to come up with you're at a crossroads where you have to take a decision on how you are going to handle these points that are outliers. We'll see one other case here. Maybe let's try out loan amount. So with loan amount, we again see that these many points are outliers. So when you put a box plot and when it shows these points, rather than directly coming to a conclusion that these are outliers that need to be removed, we can do a test, can do a check. So let's see with the test data. And you see actually a similar distribution come up. There are values that go all the way until 35,000 and there are a good number of points. So they should tell you that these points could be naturally occurring, and if you remove these points, your model might face difficulty when it comes to identifying points that fall in this region. So this is one way to check it. So the other thing is we have used different methods here. So we've done box plots, we've done these count plots. We need to be very clear of how these things work. So when you have a box plot, why are these points why are these points called as outliers? So we know that depending on the method we use, a point might be called as an outlier or a point that is not an outlier. So in this particular case, what is the method? What is the mathematical formulation that is being used in this box plot to call this point as an outlier? So these are things we have to be very clear. So up next, we are going to see a bit of bivariate feature analysis. Okay, so for the sake of demo, we're going to be seeing an error here. So I want to find the correlation between different numerical features. But you see the error, it automatically tells you that you have categorical data, but your model needs something numerical. So this issue comes up because we have categorical data. So one of the simple fixes is to ensure that we check it only for numerical data. I'm going to change it to this, and now we have it in numbers. So a better way, of course, is to also work on presentation. And here I'm going to paste a simple code snippet for it. You can see I've set the figure size. I'm going to use a heat map. And not equals to true is going to give us the numbers. This is the colors that we want. Okay. So when we do this, it presents a much better picture. And in this correlation heat map, we can make a few observations. There is a very strong correlation between the column's credit history length and the age of the person. Now, this is to be expected because older people might also have a longer history of credit. Now, what happens when we have this correlation matrix? The other thing we need to be very clear about is what exactly is correlation? What is the range of values that it can take? What happens if we have a correlation of 1? So we know that when there is a correlation of 1, that is the case where both the columns are pretty much having the same information and we don't actually need one of those columns. So that is the problem of multicollinearity. You can later on link it to how are these going to affect my model training. What are some steps I can take to mitigate the problem of multicollinearity? And this will also actually guide us with a bit of feature engineering. And if we see the values with the target column, this is our target column loan status, you can see that columns such as loan interest rate and loan percent income have comparatively higher correlation value. So what does this mean? So later on we can see our feature model training, check our feature importances, and we can come back to this and even see if these are the features that even our model found to be important. So at present we have sort of an idea that these could be the columns that are influencing the target column. So with all the methods that we saw so far as well, we are not just focusing on this particular data set, but we want to ask the question, what am I understanding from this output? How is it deciding what techniques I shall be using later? Now, previously we did the count plot for the column loan grade, and we saw that there were a few columns that were not that dominant. So now we can do it in conjunction with the target variable, wherein I'm going to print the loan grade once again, but we are going to see it separately for the two classes, whether my loans have been approved or they have been rejected. Here we see an interesting picture. In these dominant categories, even though they are dominant, so to say, we see that it is most of the loans have been rejected as compared to approved. Whereas if you take the categories D, E, F, and G, we see that here the loans are being approved, the more number of loans are being approved as compared to loans being rejected. So this should tell you that even though these categories, the overall numbers might be in the minority, they definitely have a distinction when it comes to the other classes. So it might not be a good reason to combine the two. So we'll once again see maybe a box plot as well, wherein we check for the two classes individually. So here we have the two classes, approved and rejected. And even you can see that the distribution of the income column for the two of them are quite different. So income values that are greater than say zero point 0.5 into 10 to the power 6 have almost always been rejected. So these are definitely important insights that we can make use of while building our models and even later on to analyze our models. So with this, I'm going to have one more plot that is there here. So now this is the density plot for the two classes. So we are going to take the column loan interest rate and we are going to plot the distribution by separating it for the case of approved and not approved. So here you can clearly see when the loan interest rate is higher, there is a higher chance of there are more number of loans being approved. So this again makes ties well with our domain knowledge that if the candidate is willing to pay back at higher interest rates, there could be a better chance of the loan being approved because that is a higher profit for the financial institution. Okay, so with this, we have done a bit of EDA. We have looked at features individually, we have looked at features in conjunction, As I mentioned, our goal is not to come up with a solution for this particular data set, but in general, think about how the approach will be for any data set. So, for a recap of what we have done, we started with some simple functions, understanding the columns, checking for null values, their data types, and we discussed that the data types are going to decide the kind of pre-processing that we. Then we saw the describe function. We saw they were in different scales, and that told us there could be a necessity for scaling. We saw the presence of erroneous data, and that will again tell us that we have to deal with these outliers. And then we saw that the data set could be imbalanced with this zone status column. We got all this information just by this one function. And it is important to also note it down using this markdown cell here. Then we saw there were no missing values, but in general, for missing values, we discussed that there could be different approaches. Then we saw the unique values that different columns take, and the number of unique values that the columns can take can dictate the kind of encoding method that we want to use. We would also want to drop columns which have a lot of unique values that are quite close to the actual number of rows. That is, if I have 60,000 rows and over 59,000 unique values, then that column is most likely going to be useless when it comes to giving any information to the model building. Then we saw the cases of individually looking at a few features. Here we can catch any inconsistencies or spelling errors, typos in the data while it was maybe being entered. And then we went to a bit of the EDU. So we first looked at the target column and we understood that it is imbalanced. And once we get that, we know that we have to potentially use different imbalance handling techniques. And then we saw features individually. So here we have clubbed this to a single plot, but you can always look at these plots individually and see the behavior of different categories within the features as well. So then we did some box plots with the emphasis that we should understand how these points are being called as outliers when we put up a box plot. And then we did some bivariate feature analysis where we had the correlation. We presented it better using a heat map. And the thought process is to understand what do these correlation values mean? What is high correlation? What happens if there is high correlation? How does it impact my model? What decision choices should I make? That is, which column should I drop? And then we saw of the correlation with the target variable. Can I call these as my imported variables? If there are columns with very low correlation, is it okay to drop them? So these are questions that should come up when you are actually building your model. And the only way to get answers is to keep experimenting and try out different methods and see the score that you obtain. Later on, we took the same loan grade case and we saw that even though there were a few categories that were not very frequent, they still seem to be having a very clear pattern when it comes with the target variable. So this means that we have to look at the same thing maybe from different perspectives before we actually take a call. So this was mostly some important findings. So in this one, we saw that in the feature of loan interest rate, clearly the ones with a higher loan interest are giving priority for being approved. So this was the part with EDA. And up next, we are going to see the case of validation in our dataset.